All right, so let's review stuff. Did this, talked about that, field effects, that. Okay. All right, so the next thing we're going to talk about is inverse square law of radiation. There's another field that has the same equation, and it's gravity. So what's the important part about this equation to understand what's going on with this? So what we're talking about is how much radiation am I going to be exposed to at varying distances? And so since it's the inverse square law, well, what do we mean by inverse square? What do you think? What do those two words mean to us mathematically? So inverse is what?
Flip to negative.
Not necessarily flip to negative, but whatever impact one thing has, when one thing goes up, the other thing goes down. So Boyle's law, if the pressure goes up, then the thing gets smaller, the volume goes down. So in this case, if the distance gets greater, then the intensity of the radiation goes down. So I walk away from it, I don't get as much radiation. So that makes sense. What about the square part?
Square.
Yeah, my intensity drops by a factor of a square as opposed to a linear value. Remember when we were talking about kinetic energy and I talked about slowing down in a school zone? So if the speed limit is 30 miles an hour and you roll into a school zone and the school zone is 15 miles an hour, slowing down to 15 miles an hour doesn't allow you to stop twice as fast. It allows you to stop 4 times faster because kinetic energy's velocity is squared. So if I reduce my speed by a half, it's actually reducing my total kinetic energy by a quarter. So kind of the same situation here. So if I'm receiving a certain amount of radiation, and then I am now further away, twice as far away from the source, my intensity of my radiation is not half, it's a quarter of what it was before. So if you encounter a radiation source, what's the best thing to do?
Go away.
Run away, right? I mean, you should be thinking Monty Python, Holy Grail. Run away, run away. That's what you should be doing. Just get away from it. All right, so let's do a little example here. Let's say, and that's also why it's X here and X here and Y here and Y here. That's showing us that it's an inverse. If it was a direct correlation, then the X's would both be on top and the Y's would both be on the bottom. So this is, we're gonna pull up a, where's my other? All right, so I've got a radiation source here, spewing out whatever, let's say it's gamma, and you're standing right here, and this distance is, I don't know, let's say 25 feet. And at this distance, you're being exposed to 500 millirem per hour. That's your exposure. Mind you, over the course of this year, you might receive 300 millirem over the entire year. And so 500 millirem per hour would be a significant amount of radiation. So you want to get away from that. So, all right, let's say we back up to, let's go way back here to, I don't know, the total distance now is 60 feet. So what's my intensity? So it's intensity at what was this, 25 feet intensity. Oh, let's make it easier on ourselves. Who's just right? So we'll solve for one of these, and so we'll say, I don't know, this is X and this is Y. So intensity Y is going to be equal to intensity X times distance X squared, distance Y squared. Okay, so intensity at my Y is going to be 500 millirem per hour. And my distance was 25 feet. What was going to be 25 feet squared divided by 60 feet squared. So the feet squareds cancel out, just left with millirem per hour. And so it's 500 times 25 squared divided by 60 squared. So it's so now instead of receiving 500 millirem per hour, this person is only receiving 86.8 millirem per hour. Is everybody able to drop that into their calculator correctly? Just want to make sure that you put the squares in the right spot, the carets in the right spot, so you end up with 86-ish. Okay, we're gonna pull that thing back up here in a second, but next thing I want to talk about is something called shielding. And so shielding is exactly what it sounds like. And the way that the radiation community has decided to work with shielding is they use, I guess it's a unit. It's called tenth thickness. So what this means is it's a thickness of something or other, some substance that will reduce the radiation to 1/10 of what it is on the other side of the shield. So if you're getting 50 on unshielded, and you put the shield up and it's 1/10 thickness, now you're only being exposed to 5 millirem. You okay with that? So you could put multiple layers of 10 thicknesses down to, 1/10, and then put another thickness, and it'd be 100th, and put another thickness, and it'd be 1,000th of the radiation. And so you can quickly reduce the amount of radiation by putting up the correct shielding. But what's important to realize is the shielding works differently for different radiations. So what we would shield for would be neutrons and gamma. So why am I not shielding for alpha and beta? If we remember the units that we talked about here, the quality factor for gamma and beta is 1, for neutrons is 10, and alpha is 20. So that's 20 times worse to be exposed to alpha than it is to be exposed to gamma or to beta. So why am I not blocking for alphas? And the answer is alphas can't make it through the dead layer of skin on your body. If your skin had the isotopes that are producing the alpha, that would be a problem. But if this was an alpha emitter and it was sitting right here, I would not be concerned about it. Why? Because it's going to hit me, and it's not, the alpha particles aren't going to do anything. They're going to hit the dead layer of skin, they're going to steal 2 electrons and turn into helium, and it's going to float away. It is literally not going to be a problem because it can't damage something that's dead, and the skin on your body is dead. The only way it can do any damage to you is by breathing it or by eating it. It needs to get inside of your body. So I'm not concerned about the alpha. My clothing, my skin protects me from that. But I am concerned about the neutrons, and I am concerned about the gamma. Both of those things can cause cancer. So each of these things have
completely, utterly different modes of stopping them. The gamma, you would use lead. So 2 inches of lead is 1/10 thickness for gamma. Oddly enough, it doesn't do squat against neutrons. The neutrons will pass right through it. What works for neutrons is water or plastic or jet fuel. Polymers or liquids work well for it. You can put cooking oil, bacon grease, it wouldn't matter as long as it's got something to run into. So if you're protecting somebody again, concrete also works. So if you're wanting to protect somebody against a neutron source, you would put like a 10-inch concrete wall or some kind of barrier that you'd fill up with 10 inches of water. That would be 1/10 thickness for the neutrons. Or you could fill it up with plastic, doesn't really matter. Or you could fill the tank up with JP5 jet fuel, whatever it is that you want to fill it up with. So the only two that we're concerned about is 2 inches of lead is a 10 thickness for gammas, and 10 inches of water or plastic or whatever is a 10 thickness for neutrons. So it does take more thickness to block the neutrons, but the thing that you're blocking it with is free, basically water. It's cheap. Okay, so if we have the same problem here, but on top of the math that we just did, let's say this is a gamma source. I think I said that. I put in 2 inches, 2 inches, so 4 inches of lead on the other side of this wall. So now what is this person being exposed to? The math is super easy. You just move the decimal place. So this is gamma. So lead is what does it, and every 2 inches is the 10th thickness. So when it goes through the first time, it's 1/10, and when it goes through the second 2 inches, it's 1/10 of what came through the first 2 inches. So you just move the decimal place over 2 spots, and now this person is being exposed to 0.868 millirem per hour. You put another 10 thickness in, that's less radiation than you'd be getting today on a bright sunny day. The difference is if it's neutrons, then this has to be 10 inches and 10 inches. So you need 20 inches thickness of water or concrete to block all of this to 100th of what it is on the other side of that wall. Are you okay with that? So why would you use shielding? Why wouldn't you just run away? Because running away works best. Okay, so what if you can? What if you're an operator at a nuclear power plant? You can't just walk away from the plant. You got to be there and you got to do work. You got to watch it. You got to do maintenance. So how do you deal with it? You just build giant barriers. So the nuclear plant has giant shielding barriers, whether they're concrete or they're lead, they block. So the radiation level at an operating nuclear power plant, they just finished one, came online last year in Georgia. Those guys aren't receiving any radiation by comparison to somebody just standing outside. There's that much shielding in between them and the reactor core. And we'll get really specific about locations of all that stuff at some point in the set of notes at the end. And the other issue is if you're on a vessel that uses nuclear power. So on the aircraft carrier, obviously I could only go so far to get away from the 2 nuclear power plants. So we just shield the hell out of them. Same thing with a submarine. All the submarines run on nuclear power, so you have to shield it. I don't know. Did you guys watch Hunt for Red October? 90s movie, Sean Connery. No. So it's a movie about the Russians coming up with a submarine that is so quiet that conventional hearing can't hear it, which would have been really dangerous potentially for us if the submarine was just like floating around off the coast of New York City and we had no idea, even though we've got a bunch of sensors out there. So the person in charge of that the captain of that submarine thought it would implement a nuclear war. And so
he decided to give the submarine to the United States. So they both have that technology. So more of that, like, if you kill us, we'll kill you kind of situation. But regardless, you're going around, there's this submarine battles with the two different types of submarines on each side. The two submarines are an alpha submarine and a boomer submarine. Both the Russians and the US have them and nobody else has them. So the difference is the boomer submarines is just a super quiet, slow moving truck that floats around underneath the water that's got a bunch of nuclear missiles in. So it's just supposed to literally circle in the ocean on its chaotic pattern for 3 months. You go down for 3 months, you come back up. That's it. You don't do anything. Hopefully it's utterly and completely boring. The alpha submarine's job is to go find the Russian boomer submarine so we can track those and see where they are. And the alpha submarines for the Russians were always faster than the alpha submarines for the United States. And one of the reasons why is they did a crap job of their shielding. If you were assigned to a Russian submarine, the chances of you making it to being 50 years old is pretty slim. Why? Because they would put up 2 inches of lead, 5 inches of water, and just have the guys be exposed to all that excess radiation. There's several movies about how bad the Russians treated their own sailors on those ships. And it is that bad. So our submarines were always slower because they were always heavier because they were always shielding the sub guys. Literally, those sub guys, I knew several of them from school, and they chose subs. I didn't want to be on a submarine, so you have to volunteer to be on a submarine. And they came back basically the color of that wall. Like there was no, they were down there getting vitamin D supplements because they got no vitamin D. There was zero radiation they were being exposed to. Why? Because that's how good the shielding was on the American submarines. I don't know. The Russian guys probably came back tan. Okay, so if I get further away from something, the radiation level drops by a square factor. And I could throw shielding in between me and whatever that thing is. And it depends on the source of the radiation, the type of radiation, if it's gamma or if it's neutrons, because we don't care about the other stuff because it can be blocked by our skin. Okay, so let's talk about some radiation detectors. So we've got two different types of radiation detectors. One is a gas-filled radiation detector, and the other one is called a scintillation detector. So this is a gas-filled radiation detector. That is a little, doesn't look quite like what it is. It's bigger than what it looks like. The round section is about the size of your thigh. It's specifically that big to be the size of a average man's thigh because they're trying to determine how much radiation the average man would receive if we're exposed. So the way this works is that chamber is filled with probably argon gas, but it's going to be one of the noble gases. Inside that chamber, there's going to be a single wire, and there's going to be a battery source that jacks the voltage up to around 2,000 volts. So very high. Again, the wall voltage coming out here is 120 volts. So what ends up happening is if there is ionizing radiation that can cause bonds to break, electrons to get knocked off, it will come in and it will hit the argon and knock an electron off. Well, we know argons don't want to lose their electrons. They're a noble gas. So whatever came in and hit the argon must have hit it hard. So if it hits it hard enough to knock an electron off, that's radiation that can also do damage to a person. So what happens is the electron gets knocked off the argon, and it wants to go right back to the argon. But in the middle of the chamber, there's a wire that's positively charged with 2,000 volts. So this negatively charged electron is like, well, I can go back to where I was, and that thing's got a charge of +1, or I can go to this thing that's got a charge of 2,000 volts. So it goes to the electron goes to the wire in the middle. It travels down the wire, goes through the battery source, gets counted, and then finds itself on the edge of the interior of the can. And what's waiting for it right there? Well, the edge of the interior of the can is negatively charged because the wire is positively charged
positively charged, and the can is negatively charged. Because the positive side of the battery is connected to the wire, and the negative side of the battery is connected to the interior of the can. Well, when that argon lost one electron, what was its charge? Oh, you said plus? Sorry, I thought you said less. Yes, it is. It is plus.
Plus one, absolutely. So now I've got this ion of argon that's got a plus one charge, and all around it, there is a can that's got a negative charge. So it goes and it just like hugs the can. And when it's waiting
There at the can, hugging this thing that's got its opposite charge, its electron shows back up, and then it gets it back. And so the argon is ionized, and then it finds its
charge again, it becomes neutral. So it goes, keeps going back and forth because this radiation is knocking its electron off. And so you count that. So this would be for like a high energy gamma source or a neutron source would be causing this sort of radiation. So this would be, there's some kind of exposure of core, which would be difficult, but regardless, yeah, this, lots of gamma radiation or neutron radiation. So now the question is, how do I detect for alpha and beta particles? Because this machine is useless for alpha and beta particles, because alpha and beta would just be blocked by this black canister. Can't get inside of there. So I have to come up with a completely different detector, and I will give you a terrible drawing. So here's my terrible drawing. This is called the scintillation detector. This is Mylar. Do we know what Mylar is? What if I throw the word balloon after that? Now do we know what Mylar is? Not a regular balloon, right? Not a latex balloon, but the Mylar balloon, which is kind of the crunchy ones. They actually hold the helium longer because they have smaller pores. So it's a crunchy sounding, shiny polymer. You can paint it different colors and get rid of the shininess and whatever. So basically what I have is a can, and on the on one of the sides of the can, I've got a piece of Mylar that covers up. The inside of this can is painted with a substance basically. It's a special kind of glow in the dark paint. All right. So the Mylar is blocking visible light from getting in, but it doesn't block alpha and beta particles. So if an alpha or beta particle were to make it in here, so I got an alpha particle, it comes in and it slams into this. What it'll do is it'll cause this to glow. It'll cause it to glow its yellow color. So you get radiation, yellow radiation coming out from this. And then what I've got right here this is a detector that detects just glow in the dark color. So if there's any glow in the dark happening inside here, this detector right here detects that. And then there's a counter or a device that measures how much radiation, how much glow in the dark light has been received by this radiation detector. And that's how we do it. So a scintillation detector is usually something, it kind of looks like a shower head, one of those shower heads you can pull off and spray yourself down with. So if you exit the reactor room, you would have to go through this process where you take the scintillation detector and you just run it across your body slowly. And if you would somehow become contaminated with some kind of substance, I mean, it's definitely possible that there was dust inside the reactor room. That dust could become radioactive, and you don't want to carry that around with you. So if it was on your clothing, they'd make you take your clothing off, you'd get rid of that shirt or whatever. But ultimately, the reactor room is quite clean. The filters on it are good, but all of that is still possible. So you would use this scintillation detector to check for any of those things. This is also the same kind of thing that they would use if somebody got somehow contaminated and they took them to a facility. You'd have to take them to a special hospital that had one of these things. So, do you guys know what DARPA is? I feel like we've talked about it at least once. It's the branch of the Pentagon that pays people and companies to come up with James Bondy kind of stuff. Things that they need. So they want something. And so they put out like, we'll give anybody $10 million that they can do this. That's how GPS was born. DARPA put out a request for proposal. Somebody developed GPS. They bought it. And then for a long time, GPS was a thing. And then the public got access to GPS, but it was kind of crappy GPS. You were only able to sell a GPS detector that was within 100 meters of what the GPS really was. So, I mean, that's 3 football fields away, a little more than 3 football fields. So they didn't want it to be any more accurate than that. And then now it's, you know, spot on because they decided it doesn't matter anymore. So you can just have it. So the reason we're talking about DARPA is because DARPA asked somebody, how can we easily detect alpha and beta particles for our basically sailors that would be operating nuclear power plants? And so this machine came up to be. And so the cool part about this is this machine was developed, and what this thing does, this detector, remember what it does is it will detect any glow in the dark color light. That's it. And so this one specific wavelength, it would be, I don't know, let me think about that. Somewhere probably around, maybe around 650 nanometers. That's all it can detect. Nothing other than 650 nanometers. Everything else would be dark to it. It wouldn't see any of that. So once this first detector was detected and this was developed, and this was in the 40s, could have been the early 50s, late 40s, early 50s, that this detector was developed. Then the companies that had access to this started to wanted to commercialize it. So just like GPS was a way for the military to identify where their people were and where their targets were, and then the GPS became, you know, it's in your phone and it tells you how to get to Rite Aid. The same kind of thing happened with this detector. What is this detector detecting? Is it detecting alpha or beta particles? No, it's not. It's inferring alpha and beta particles based on the fact that there is glow in the dark. If you took this Mylar away from this and regular light came in, this thing would be glowing like crazy because regular light can cause the electrons to bounce up for glow in the dark paint. So it doesn't detect alpha and beta particles. What it detects is 650 nanometer yellow light. Okay, is that useful? Yeah, but not super useful. But what if instead of it being able to detect 650, it could detect a range of 700 nanometers down to 490 nanometers? What if it could detect any of those? It took a long time. It took like, let me think about that, 40 years, but it happened. And so what is the result of the development of this scintillation detector? What do you use possibly on a daily basis that is the result of this research? What does this thing do on your phone? It detects light. So all digital cameras are the great-great-grandchildren of this device. So when I've got a sensor on your phone, obviously this is much bigger than the sensor on your phone, this little pixel right here, and instead of just being able to detect yellow light at 650 nanometers, that pixel right there can tell you any color from red all the way up to purple. That one right there. And then you can increase, what we've been able to do over years is increase the sensitivity of this. So is it 650 nanometers or is it 649 nanometers? Because it might not seem like a big deal, but it makes it so the digital cameras look more and more true to what the actual color is. So as we improve on these products, these little dots, two things happen. They will more correctly identify the wavelength of whatever the wavelength of light that hit that one spot is. It can identify that color, and the spots can get smaller. So if the spots get smaller, then the dots get closer to each other, and then this thing is there's a higher resolution factor with it. Do you guys know what dotism is as a form of art? Do you know what the New York Times, how the New York Times produces their images? Do we even know what I'm talking about?
That's creative image.
Yep.
Yes.
So usually when the New York Times puts a picture of somebody up, these are, man, I've gotten so good. That's just incredible. Can't even find an old one. They're so fantastic. I know this is going to sound, it's going to be a little bit ridiculous. Open image, a new tab. This is way better than it ever was. This was drawn by using dots. So if you zoom in close enough on this, you'll actually see it's Minecraft. There are no everything is not connected. They're all individual dots, but the dots are so small, your eye can't pick up the resolution difference between them. In Minecraft, it's easy. Everything's got corners. But if you look at like a modern or a more modern video game, you can't see that really the shoulder of that character is just blocks because the blocks are so small. So that same situation with this scintillation detector, this scintillation detector used to be good size and could detect one color, and now it can detect all colors. It's ridiculously small, and you can fit like 1 million of them across this. So that's why all the digital stuff, images, at some point, maybe 10 years ago, the digital photography was better, higher resolution than or just as good as regular old film photography. And you didn't have to deal with the fact that it's film and you got to go get it processed and created and whatnot. So it literally became just as good. I'll find one of those New York Times images and post it. So in the same way that canning was a result of a military endeavor, digital photography is a result of a military endeavor. Same situation with GPS. So military bad, but also it can help spur progress, scientific progress. Okay, so I know we did a lab on Half-Life, but I want to get super specific about Half-Life. And so that first question, I think the first question was, what does Half-Life mean to you from that lab? So what did you guys write down?
For half of something to produce something else.
Perfect. Time for half of something to turn into something else. So if you start the month with a certain amount of money, how long does it take for your checking account to have half of that money? That would be its half-life. And it depends on what's going on. And in this case, it depends on what element we're talking about. So for half-life, as far as chemistry and physics is concerned, is I've got something that's radioactive. How long does it take for half of that radioactive substance to convert itself into a different substance? So my example here is this protactinium-234. The protactinium-234 has a half-life of 72 seconds. So if I start off with 500 grams of this stuff at time equals 0, after 72 seconds, I've got 250 grams of that stuff left. There's half of that protactinium 234 is gone. And so in the time column, I just keep adding 72 seconds. I don't double it or anything like that. It's 72, whatever I got, plus another 72, plus another 72. The substance doesn't care what it used to be and what it will be. It only cares what it is right now. And then after 72 seconds, you'll have half of that stuff left. So this is 1, 2, 3, 4, 5, 6 half-lives. So 72 times 6 would be 432. And you can see it's gone down by a half, by a half, by a half, 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 and it's half of what is left. So a question could be, how long does it take to decay to 10 grams? A question could be, how long to get below a certain value? So in this case, I don't know what the 10-gram value is. I know it's somewhere between 630 seconds and 432 seconds. That's when I'll hit 10 grams. All right. But there's also some math we can do. So we're going to do that math. And copy, go over here. What is going on? Are you frozen, Microsoft? It's been- So this is the half-life equation. The T is time. There's a negative sign there. And then it's T 1/2, which is the half-life of the substance. The half-life of the substance has to be measured. It is not something that we can figure out using some kind of math or theory. It's literally, I got some stuff. I measure how long it takes to have half the stuff. So all of those half-life values that are on your periodic table are on that periodicity chart, nucleotide chart on the right as you walk in on your right-hand side in the lab. That's all experimentally determined. Then I've got the natural log of 2. And then I'm going to multiply that by the natural log of the fraction, what I got divided by what I started with. So the N is moles, I guess you could say, and then moles original. So my half-life, my original amount, sorry, my final amount and my original amount. And then I can determine how long this is going to take. So let's do that, figure that one out. So it's negative, and my half-life was 72 seconds. And then this is the natural log of 2. And then this is time, the natural log. And then I'm curious about how long it takes to get to 10 grams. I started with 500 grams. And so now, what do we got into this? So we've got negative 72 divided by natural log of 2 times, I'm sorry, we have a natural log problem. Natural log. There we go. Natural log of 2. Natural log of 2. Parentheses, and I get 406.4 seconds. Sure, that's what I have. Oops. Sure. Okay. Again, I want to make sure everybody can type that and get that value. Are we okay with that? So that's one question that could be asked. How long does it take for the sample to get down to a certain value? The other question that can be asked is, I got this stuff, and what happens if I wait, a year? How much do I have left? So then I got to do some math with this. So we're gonna solve for N. I want to know what N's value is. So I'm going to know the time, I'm going to know what I started with.
And so we're gonna figure out where, how to solve for n. So mathematically, the first thing I'm gonna do is multiply both sides by a natural log of 2. That disappears. Multiply both sides by -1, so that goes away, and there's a -1 here. Divide both sides by half-life. So at this point, I end up with negative natural log of 2 divided by half-life is equal to the natural log of n divided by n ho. Are we okay with that algebra? Literally just flip the fraction and move the sign over. How do I get rid of natural log? Because I need to isolate n. So I need to get rid of the natural log on the right side. Do we know what the opposite of natural log is? It's e. It's the e that probably looks like that on a calculator. Not the capital E or the capital EE. Is it drawing 4 lines? But the little e, and it's probably associated with they're probably the same button, natural log and e. It's probably the second function of that same button. So if I take e to the x of this side, the natural log goes away. But all this stuff on this side is now the exponent to e to the x. That's how that works. So my next derivation would be e with an exponent of negative natural log of 2 divided by half-life is equal to n divided by no. So then it's just multiply both sides by no. So I end up with n is equal to no times the natural log of negative natural log of 2 divided by half-life. Where's my time? Times time. Forgot time up there, sorry. Times time. There we go. Time. Okay, so we're going to use that same substance, except we're going to wait, I don't know, let's wait 400 seconds. All right, so let's look at this for a sec. So we're going to wait 400 seconds. So can you guesstimate how much mass should be left after 400 seconds? Somewhere between 15.6 and 7.8, right? Just so you know that your answer needs to be between those. So you can always get a guesstimate by throwing up one of these tables really quick and being like, okay, so I know my answer has to be in between these two numbers. All right, so what I got here is 500 grams times e to the natural log of 2 times 400 seconds divided by the half-life, which was 72 seconds. So this is another, can you punch it into your calculator thing? So 500 times e negative natural log of 2 times 400 divided by 72 close parentheses. That makes sense because we had just calculated that 10 grams took 406.4 seconds. So if I only waited 400 seconds, I've got 10.63 grams. You okay with that? I'll give you a chance to do that on the homework. Anybody have any calculator issues? Okay, so let's talk about radioactive dating. So we got this same question, right? The same calculation. We do.
I'm not all of a sudden not allowed to write. Yeah, that was super weird.
So if I wanted to date something, determine how long it's been around, what, if I did that, I could, I need to know how much is left. So I need to be able to actually take a measurement to figure out how much of some radioactive material is left. And I need to know about how much there should have been originally. And then that can tell me how long that thing has been around for. And so we do this with, like, somebody finds an ancient bowl. They're in Samaria and they found some bowl, and it's a wooden bowl or a wooden spoon or something like that. They want to know how long that thing's been there. You can do radioactive carbon dating. So right now we all have a certain amount of carbon-14 in our body. There's a whole bunch of carbon in our body, and a small percentage of that carbon is carbon-14. So we're all emitting some kind of radiation associated with the carbon-14. When you die, you stop eating carbon, and so you stop incorporating carbon into your body. So you're born, you got a certain carbon level, and it just stays that way during your entire life. And then after you pass away, the level starts to drop because you're no longer eating anymore, and that's decay. You're not replacing the decayed stuff. So if a tree was cut down, fell down, whatever, and then it was turned into some kind of tool, then that tree is no longer bringing in carbon-14. So it's just going to lose its carbon-14 over a certain period of time. And it produces, let's look at its time frame. Carbon-14 has a half-life of 5,730 years. So this isn't going to be super accurate. It's not going to tell you like what month 10,000 years ago it disappeared, but it can give you a rough estimation within 5 to 10 years of how old the thing is. And so this works for about these years. So what ends up happening, why doesn't it just continue to work? And the reason it doesn't continue to work is you guys did a lab with it was a graphing lab. I had to put 9 molar hydrochloric acid in water and then graph it. I just wanted to make sure we knew how to use Excel or whatever correctly. And the first example problem I had for you was a nuclear decay. So this is what the half-life thing looks like. So after a certain period of time, you've got half, and you got half of what you had, and half of what you had, and half of what you have, half of what you had. And so eventually, it would be like me saying, all right, so get halfway to the door. All right, get halfway to the door. Get halfway to the door. After you've done that 5 times, halfway to the door is you barely moving anywhere at all, right? So that's what's going on here. Once I've reached about 6 half-lives, 5, 6 half-lives, the amount of radiation that's left from the original is so small that it's hard to detect. So it depends on where you do it. We've got a couple of places on the planet that are in incredibly good spaces to remove background radiation. We have these holes. There's nothing else to say about it. Holes. And there's a room at the bottom of the hole, but around the room, it's filled with water. So the water is a very good way to block radiation. So you can do very sensitive background checks on things. So right now, if we were to do carbon-14 check on something that was 40,000 years old here, we wouldn't be able to do it. Why? Because there's so much, like this room would be spewing off so much carbon-14 at these small levels that you'd be reading background radiation. So you wouldn't be able to detect it. But if you took it to one of these isolation rooms, you could detect it because there isn't any background. There's very, very little background radiation. Those rooms were developed to do that. They were developed to do when we were searching for neutrino and now searching for gravity waves, things of that nature. But they decided we could use it for other stuff. So if we wait long enough, it won't work anymore. So carbon-14 dating, we can't use carbon-14 dating on a T-Rex bone. Why? Cool. Humans and T-Rexes weren't around at the same time. So humans went around for 1 million-ish years. These things are much older than that. So how do I figure out how old a T-Rex bone is? I would use a different ratio, like
this potassium ratio. So we've all got some potassium in us. We talked about this last class. Potassium 40 is radioactive. And so all substances should have a certain amount of potassium 40 based off of the isotopic ratio of potassium on the planet. So you would expect an organism to have a certain level of potassium in it, and thereby a certain percentage of that be potassium 40. And so you can easily check the age of something very old because the half-life is, 1.25 billion years. So it can detect, can figure out approximately how old within like a few million years of these bones are. And a few million years might seem like it's really off a lot, but it's really not off that much when we're talking about the time frames. So could be just a couple of percent off of when it actually died, which could be million or hundreds of thousands of years. We also use this to determine how old asteroids and meteors that have hit Earth are. So have you guys seen any asteroid impacts? No? Have you seen any of those? I think the best one, literally for me, the most obvious one. This one in Arizona, and it's got a great name. It's called Meteor Crater. That's it. So for a long time, nobody knew what it was. And then when geologists came to the scene, they were like, okay, so we have some kind of weird volcanic steam explosion here. Is this like the top of Crater Lake? This Crater Lake was a volcano and blew its top off, and now there's a big lake up there. Is that what it was? And some other scientists were thinking, well, maybe we got hit. And so that's kind of terrifying, right? The idea that we could be hit by something. And at this time, late 1800s, early 1900s, the church was still in hardcore grasp of everything. And nobody wanted to think about that because nowhere in the Bible is the word meteor written or asteroid written. Nobody had the idea that we could be annihilated like the dinosaurs were. And so we didn't want to think about that. So it took some pushing to realize that this is the result of some kind of meteor hitting us. The way that they figured out that it was meteor hitting us was two ways. One, they found some weird rocks, and then they checked the ratios of Sumerian to neodymium in those rocks. And those rocks were way, way older than Earth. Earth, 4.5 billion years. And these things were in the tens of billions of years old. Okay, so these things are much older than us. And the other way is open in a new tab. That's not what I said. Stop. A guy named Eugene Shoemaker, who was a geologist, who was super interested in space and in Earth, found this. This is a mineral called cosite. We can't make cosite on Earth. It is made under incredibly high temperatures and pressures. Only those temperatures and pressures have only been seen when something hits us. So at these temperatures and pressures with silicon and some other minerals, you can get this glassy kind of mineral called cosite. So after Eugene, basically him and a couple of other people proved that this thing is a meteor site, the rest of the world was like, well, are there other meteor sites? Like, is this a common occurrence? Like, what's going on with this? And so he would be commissioned by countries to come and say, hey, so if you airplane fly over this thing, it looks like maybe there was a meteor here, and there was a really good one in Austria
where flew in on a small plane, was like, oh yeah, that's a meteor impact. Landed, got into a cab, drove into the middle of town where he was supposed to meet with people, got out and was like, that church is got an interesting stone exterior. So he walked up to it, and what was on the exterior? It was rock embedded with kozite in. So he could definitively say this rock came from rock that was hit by a meteor because it's got this stuff in it, and we can't make this stuff on Earth unless it gets hit by something. So we can determine ages of things based off of half-lives, and then you can also do some mineralogy. He was supposed to go to Mars. Sorry, he was supposed to go to the moon, and he got the measles, so he didn't go. Obviously, very sad about that. But then there was also another group of people who didn't think that the meteor things was still an issue, and like we couldn't be hit by stuff like that. Nobody had ever seen it happen, so they're still denying that kozite and the half-life thing was an issue. And then he, his wife, and his best friend had a, I don't know, like a $10,000 telescope that they were watching the stars all the time. And they actually found a meteor, a trail of meteors that had passed through Saturn's rings and produced this particular light. They did some calculations and realized in a couple of years that's going to hit Jupiter. So they told everybody and said, these are going to run into Jupiter. And so we were actually able to visually see meteors hitting another body because we haven't seen that. And so he definitively proved it in many different ways that meteors do in fact hit stuff, which is, I mean, it's dumb to even think it doesn't, right? The moon doesn't look like it does because it was formed like that. It got hit by stuff. So there's lots of different ways to determine how old something is based off of half-lives. And this one is kind of important to us. What was special about uranium-235? There's a small amount of it. It's the fissionable uranium that's on that can work. The uranium-238 is the non-fissionable stuff. And these things both have half-lives of millions of years, right? This is 4.5 billion years. This one here is 704 million years. So when we produce radioactive waste, we're talking about millions of years on those half-lives. Does anybody know what we're doing with it? We should have buried it, but a Senator Reed from Nevada, stopped that from happening. Why would Harry Reid stop that from happening? Where was the place we were going to bury it? It was in Nevada. So he did a little bit of NIMBA, not in my backyard, and stopped that from happening. And he's actually not a senator anymore. He's actually dead, and they still haven't decided to use that facility. We spent several $1 billion building a facility underground, and they trumped up some geological stuff that said it's not a safe place to put it, which is complete and utter garbage because it is a safe place to put it. So now when you apply to operate a nuclear power plant, there are a lot of like licensing fees, a lot of like, what are those called? SDCs, which are charges by local and federal governments to provide services. One of the things that you get charged is a fee for the federal government to manage your nuclear waste. And so you produce nuclear waste and you have already prepaid for them to take the nuclear waste away and put it in a storage facility, except we don't have a storage facility anymore. One of the storage facilities was Hanford, Washington. And what's wrong with that? Those tanks that are like 80 years old have rusted. And that radioactive liquid makes its way into the Columbia. So downstream of Hanford, the radiation level is 100 times upstream of Hanford. So we don't have a good place to put it. So what are they doing with it? They're literally putting it in concrete containers and just leaving it on facility. So all the nuclear waste that's being generated is being kept on site. At some point, that's not going to work anymore because they just won't have the space for it. And it's fairly safe. But it's only fairly safe. If they were to just take this stuff and put it in this cave in Nevada where they were supposed to do it, everything would be fine. The other thing that we could do to it is we could take it to space, but why are we worried about that? I mean, literally, you could take it up to space and this astronaut could just sort of like kick it towards the moon or the sun and it would eventually make it there and the sun wouldn't care. But why is that not a great idea right now? What would you be worried about with a rocket filled with nuclear waste flying up into the sky? It'd explode. Then like all of southern Florida or Texas is covered in radiation. So can't do that. We're not going to do that right now. We will at some point create a geosynchronous platform. Stuff. What's that mean? What's geosynchronous mean? It's in sync with the earth. So if you get a satellite dish, you point it over there. Why? Because the communication satellite for Dish Network is over there. How is it always over there? Because it's in geosynchronous orbit. We threw it up there and we gave it just the right amount of speed to just spin with us at the same speed. So it's got to be spinning a lot faster than us, right? Because it's further away from the center, but it's got just the right amount of speed so it just stays right where it's supposed to be. It's not like it's got guidance rockets that adjust it every once in a while. It just stays there. The math on that is pretty easy for somebody with math brain. So what we can do is we could build a geosynchronous platform. And from that platform, we could drop down a cable and connect it to a geosynchronous spot on Earth. And then you could have something crawl up the cable. So when we do that, once we get that thing built, which will still be quite some time, then we could put the nuclear waste in canisters and have it just climb up, and the canisters could all have like a parachute on. And if something happens with the rope or something happens, there's a lightning storm or something, or the canister falls, it's just got a parachute on it. You just get it, put it back up there. But until we get one of those spider crawling rope thingies, we're just leaving it on site because we're dumb about what we should be doing with it, which is putting it in that damn cave in Nevada. All right, so next thing I want to talk about is this thing called a decay series. So what we have here is Z, which is the symbol for the proton number, and then this is the N number, the neutron number. And so I've got myself some uranium-238, and these guys have half-lives. That's what these things are. So billion years, 24 days, 1 minute, 25,000 years. You can see all of these different things, all these different half-lives, until we get down to this lead that doesn't have a half-life here. So lead 206 is not radioactive. It's stable. So if you start with uranium, and there's a bunch of uranium on the planet, and if you wait long enough, what will happen? It'll turn into lead. It'll literally turn into lead. So uranium-238 will become lead. Great. Okay. So this thing has a half-life of 4.5 billion years. The Earth is about 4.5 billion years old. Half of the uranium-238 that's on the planet is gone. So the amount of uranium-238 on the planet is dropping. The amount of lead-206 on the planet is going up because it's being turned into this lead-206. So what are these different, like, why is it going up and down? Look at these numbers. So as I'm moving this direction, what's the x-axis telling me? Less neutrons. Less neutrons. These isotopes are getting lighter and lighter as I move this direction. Okay. What about as it falls along the y-axis? Less protons. Less protons. Okay. So I lose mass, I lose protons. Alrighty. So let's just start here at the beginning. Got my uranium-238. And the weird part about the uranium-238 is it turns into uranium. So how's that happen? So what has happened here? I have my first nuclear decay turning into thorium. So what process happened? I got a nuclear transformation.
right? It is converted to a new element.
Alpha.
It's an alpha decay. Are we okay with that? Because this is uranium-238 and its atomic number is 92. This is thorium and its atomic number is 90. So it lost 2 protons. It also moved this direction and lost a total mass of 4. So that means it lost 2 neutrons. So it lost 2 protons and 2 neutrons. So that's an alpha decay. So every time it goes at this angle, that's an alpha decay. But what's happening here? That's a beta decay. So the beta decay is one of the neutrons spitting out an electron out of its nucleus. That neutron turns into a proton. So the mass number doesn't change, but the proton number goes up by 1. So down to thorium, up to protactinium, and then back up to uranium. So I've got a nuclear transformation, and overall I lost a total mass of 4. And how long did that take? Well, the first part is a billion years, and then 24 days, 1 minute, and 25,000 years. So these numbers right here, where 25,000 years seems like a long time, but it's a, that fast compared to 4.5 billion years. All right, so then thorium, radium, radon, polonium, astatine. So remember I said there's like a teaspoon of astatine on the planet? It's because it's got a half-life of a day. And the interesting part about polonium is it could split into this version of lead, or it could turn into astatine. And then they find themselves both at bismuth again. So that's an alpha decay or a beta decay, and then it's got to do the opposite. So if it did the alpha decay first, then it would do a beta. Or if it did the beta, then it's going to do an alpha. And so then I've got bismuth, and it can do that split again, go back to polonium or go down to thulium, and then come back up to lead, and then go to bismuth again, and then polonium or thulium, and then finally to lead. So it doesn't matter what its pathway is. Eventually it makes its way to the first stable element, which is lead, which is less than 83 protons. It's got 82 protons, and that's why that lead can be stable when the rest of these leads aren't, or less of these substances aren't stable, even though we hit lead twice. Both those proton to neutron ratios were bad. Too many neutrons, just the right amount of neutrons. So my question is, besides the lead being stable, which one of those substances is not like the other? Talked about it last class. It was part of homework 12. True and false thing. Yeah.
Oh. It's a little.
It's a gas. The rest of those things are solids. Where do you expect the uranium to be on Earth? In the ground. So are you worried about any of those radioactive substances? No. I'm shielded by all of those things because the ground blocks it for me. Except it doesn't block radon. Why? It's gas. It's also a noble gas. And that's the real problem. If it was any other gas other than a noble gas, it would react with the minerals in the water in the soil. But it's a noble gas, so it doesn't react with a damn thing. So it literally just makes it through the dirt and rock and comes up to the surface. Is that a problem? Could be a problem. Does anybody know what, anybody lived on the East Coast? Nobody lived on the East Coast? There's a monumental difference between East Coast houses and West Coast houses. And the major difference is they cut down all their damn trees a long time ago. Not all of them, but they cut down the big trees a long time ago. So when they build a house, what do? To make the house bigger? is annoying as hell. Stop moving. You want a bigger house, but wood is super expensive. So what do? You build down. All the houses on the East Coast, not all of them, but almost all of them have basements. It's like that's where the term man cave came from. Just send the husband down to the basement and he hangs out down there. And then they would carpet the whole thing and put a TV in and whatnot. So, this is Reading, Pennsylvania is about right there. There's a section that has a weird issue with lung cancer. So do you guys know what an epidemiologist does? Studies epidemics. Okay. So do we know what the thinking on cancer was in the early 1900s? Like how you got cancer or what cancer could do or the communicatability of cancer?
A lot of like other sicknesses, was that the?
They just assumed that it was like everything else and it was communicable. So when you found out somebody got cancer, you're just like, I want to catch your cancer. No joke with that. So we had basically, I mean, obviously it had been here forever, but we had basically just, people had started aging to the point where you could die of cancer. Like we didn't really think about somebody dying of cancer 100 years before that, because you just died of probably a bacterial infection long before you could ever age to, I don't know, liver cancer or lung cancer. So epidemiologists started studying cancer and they would put all the dots of all the cancer all over the map of the United States. There was like a thing that kind of did this. There was a little bit here, a little bit here, some over here. And then there was this crazy. So if you're an epidemiologist and you're like, okay, so where are the cancers? And you look at this map, this heat map of cancers across the United States, reported cancers. You're like, okay, so Colorado's kind of a problem, Wyoming's kind of a problem. There's a spot in Oregon, a little spot in California, and then what in the hell is going on in Pennsylvania, Virginia, West Virginia? This dense concentration of radiation. So you might think, okay, so lung cancer, so we're talking about PA, West Virginia, and Virginia. So maybe it's coal mines, but there's coal mines here, 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 and here, and they were outside the heat map for this lung cancer. All right, so I promise I'm going to tie all this together, but come on. We'll trip the hallway. Permeable section. Incredibly high concentration. So tell me what's happening in that section. It's like. Radon is you stand there, radon is seeping out of the soil. You just have a problem, you're outside, look. Imagine. But if you're in a basement. Yes. So why are all these men dying in their late 50s of lung cancer when they're not smokers and they don't work in a coal mine? And that was really the issue. So the issue is you got your house, don't have enough wood, build your basement down here. Guy's hanging out down here so he doesn't annoy wife. radon seeps in, and now you've got radon in here. It's only got a half-life of 4 days. You breathe it in, it decays. So the 4 day half-life might seem good, but it's actually quite bad because that means once it gets into that space, you're going to breathe it in, and the chances of it decaying are pretty high because it's got a half-life of 4 days. So if you spend your time down here watching the Steelers football games, you're going to get lung cancer. So in Pennsylvania and on the East Coast, if you want to sell a house, you have to do a radon test. They send you out this little hockey puck looking thing. It's got a carbon filter inside of it that absorbs stuff. You just leave it there for a week, you send it in, and then they measure how much radon is in this little cartridge. Depending on what it is, they might have you do a radon abatement. So 2 things have to happen. The house that we lived in, this did happen. They went in and they ripped everything off the walls and the floor, and they coated it with this plastic, like rubbery, plasticky stuff. So what that was supposed to do is make it airtight. And then they also cut a hole here, here, and here. And they put a vent fan up top that had a battery backup on it that ran 24/7. So it would ventilate any radon that did get in there, and it would prevent the radon from getting in the first place by using all of that polymer stuff to coat it. Why was there a decent spot here, here, and here? You can see those. Decent spot here, here, and here, because I mean, we live right here.
Say volcanoes.
Volcanoes. This is all about elevation. It's all about stuff coming up. So have you guys ever seen that the map of Pangea in motion? First off, do we know what Pangea is? Okay, so map of Pangea in motion. So everything gets moved out to their spots as the plates move. And then there's a time lapse of all the different continents. If you watch the time lapse of the United States, it's pretty cool. The Appalachians were actually like 5,000 feet taller than the Rockies. So you have this mountain range build up here, and then erosion, wind and water just knock it down. And then as this is getting to, I don't know, it's smaller than the Rockies height, then the Rocky Mountains build up. So where's that soil coming from to build up the Rocky Mountains? Dirt, underground. So what's in the dirt? Radiation. So now there's more radiation in Colorado for 2 reasons. One, you're going to get gamma radiation because you don't have as much atmosphere over you, and the soil is basically new to the top of the earth. And when I say new, it's like several million years old, but that's new compared to like this soil here. I mean, these mountains were like K2 height and got knocked down to, 4,000 or 5,000 feet at the tallest. And so now we've got a bunch of new soil here with a bunch of radiation in it. Same situation for us. So soil comes out of a volcano and fills up. Why are there apples and pears and even peaches and blueberries in Hood River Upper Valley? Because the soil's rich. Why? It came out of the earth and flooded that. The last time that volcano really erupted, the lava went all the way up to Underwood. Do we know where Underwood is? Underwood's on the other side of the Columbia River. That if you're standing in Hood River and you look across the river to the left, the highest point over there, that's Underwood. That's that little town, Underwood. Not joking when I said the lava came down through the entire Hood River Valley and then crossed the Columbia and went up to Underwood. All of that is new soil. So if you live in Hood River in the Upper Valley, if you live in Hood River anywhere, you could have you could be on top of a bunch of soil that is radioactive. Same situation. You need to do a radon test for that. And then you might need to do abatement just because it's soil that was deep in the earth and now it's not deep in the earth. So buy a house, check for radon. And you're not responsible as the buyer to abate. They are required by law to abate. And you can, even if you're not required by that location, it's so weird about like your house might need it and your next door neighbor might not need it. So make sure you get that test. The test is like $30. So do the test. And then if it comes up positive, the seller has to pay to do the abatement.
All the dumb things you learn in this class.
It used to be in the basement in middle school.
You used to be in the basement?
Yeah, for like 3 years, so,
You still have that house?
no.
Okay.
Not anymore.
Okay, so what kind of medical applications do we have? Well, you get cancer, there's a couple of ways to kill the cells. One is chemo, which is chemistry. And so, does anybody know what chemo, the general idea of how it functions? It kills the mitosis cells. If the cell is undergoing mitosis, it kills it, which is problematic, seeing that you create hundreds of thousands of cells per day that are healthy. But if you're a cancer, it's constant mitosis. It never stops turning itself into a new thing. It never stops splitting. So you kill all the things that are splitting, which, I mean, it's a poison. It makes you sick. It makes you sick because all the new cells that you just created, you killed. So not good. The other thing you could do is you could hit something with radiation. So if you can target exactly where the radiation is, let's say you can't cut it out, you can input, or let's say you don't want to cut it out. What's the number 2 cancer for men? Would be prostate cancer. I'm saying for men because women don't have a prostate. So as a guy, if you got prostate cancer, that's terrible. You could have it cut out so you don't die of prostate cancer, but then what happens if you cut out the prostate? There's no more sex. That's done. You're finished with that. So if you're willing to do that, that's fine. If you're not willing to do that, then the only option they have is radiation treatment. So what they do is they put some very radioactive substances, which sounds super counterintuitive, right next to the prostate to kill all of the mitosis cells. And so the cancer cells can be killed. A whole bunch of prostate cells can also be killed. The radiation itself that they use for the prostate treatment doesn't typically make cancer cells. It's so powerful that it just kills everything that it runs into. So that's the real problem with radiation is it doesn't kill the cell. It changes the cell in a way that causes problems down the line. So if you hit it with a radiation that instead of, just slightly messing with something, it just flat out kills it, then you're okay. Does that make sense? So that's how that works. Well, what if you had brain cancer? You don't want to forget, your family. You do something like this. You can inject something in that's radioactive, that's got a very short half-life, that kills everything it gets near, and hopefully it's killing all the radiation cells. So we can use it for radiation. We can also use things like a radiation treatment, and this looks terrible. But have you caught a piece of wood on fire with a magnifying glass? So you can just magnify the rays and put them right and pinpoint them in the same way that glasses will focus whatever, same way your cornea is focusing things down onto your retina. Well, X-rays and gamma rays, they're light. They operate exactly the same way visible light does with a magnifying glass. So if you magnifying glass the radiation down to a pinpoint spot, and it could be very small, like in the micrometer size, you could pinpoint it right into a spot in a person's brain. It would literally fry that section of the brain in exactly the same way you could catch a piece of paper on fire, but it's killing just the spot that they want it to be killed. So you got to be like, the person can't move. You got to know exactly where you're going. You have to have the focusing exactly right. So there's a lot of scariness inside it with this treatment, but it could sometimes be, inoperable brain cancer. So they can't operate, but they could basically zap it with some gamma rays and kill everything in the area. Obviously, X-rays are super useful to us. We can find out where a break is. We can find out where other specific things are. Kid swallows a magnet, whatever, you can find it. Any kind of metal stuff. Radio tracers. So let's say that a person's having trouble with their weight, or either they're too heavy or they're too light. Could be a thyroid problem. And so a way to check the thyroid is to give somebody a small radioactive version of iodine. They get that injected into them, they wait, and then they wait for a very short period of time. And then they use a radiation detector to determine where this radioactive iodine is. Where is iodine supposed to be in the body? It's supposed to be in the thyroid. Your body takes iodine and puts it into the thyroid. What if your thyroid isn't working? They won't do that. So if you have a healthy thyroid, when you get injected with the radioactive iodine, you should be able to take a radiation detector and it should go bonkers when it gets near your thyroid. And you put it near your knee, nothing happens. But if your thyroid is not doing any iodine uptake, then the radiation is basically identical throughout your entire body. And then you know, all right, so the thyroid is not uptaking iodine. So that's you will know in 2 minutes if it's working or not. You can do that same exact thing with other substances to determine stuff is going where it's supposed to be going. Yeah, that's about it. I mean, the CAT scan is just an X-ray. But do we know what happens with the CAT scan? It's an X-ray. They move you like a half a millimeter, X-ray, half a millimeter, X-ray, half a millimeter. And so you basically just get like 300 X-rays. And then each one of those is a section of your brain. Or, you know, whatever it is that they're doing, it's usually the brain. And so then they can get a 3D image of what's going on with the brain. So lots of X-rays with that. How about some scientific applications? So atom tracker. We can take a substance, make it radioactive, put it into a molecule, and then track where the molecule goes. So let's say that we wanted to know all the places that vitamin C is uptaked in the body. That would be a dumb one. D would be a dumb one. Okay, let's say vitamin E. So we take some vitamin E and we replace one of the atoms with a radioactive isotope with a short half-life. And then it doesn't even need to be radioactive. It could be just a different isotope. So instead of it being carbon-12, it's got carbon-13 in it. So then you take the vitamin D, you wait, you allow it to be incorporated, and then you test different places, samples, and you check, is there a higher concentration of carbon-13 there than should be there? And then that can tell you where stuff is. So that's a way that we determine if a drug is going to the target location or not going to the target location. It's basically like putting an ID tag on it that then you can check later on to see where that thing went. We did this same ID tracking thing with to prove that DNA is so I got a DNA, double strand of DNA. The double strand of DNA splits and makes a copy of itself. So the question was, do the original pieces meld back together to form their original DNA strip, or is each of the copies have one piece of the original? And so we took some nitrogen, we made it radioactive, we put it in a DNA incubator, we allowed it to do its thing, and then we checked. And what we found was the radioactive stuff was only on, it all had radioactive stuff in it. Half of it was radioactive with the first round, and then all the rest of them had radioactive stuff in them after that, basically, except for the 2. So we can track exactly where this stuff goes. So it's our way of, like, if I want to know what the reaction mechanism is for some substance in your body, I can tag it with a radioactive isotope or an isotope that has a different number of neutrons than normal, and then I can follow it through your system. We're also super curious about making new stuff. This is kind of slowed down for us, but we've got this. These are all the stable isotopes that we know of. These are the yellow ones are the isotopes that we've made that are unstable. Stable meaning it's got like thousands of years worth of stability, which is why the uranium stuff is up here. And then this green stuff area here are areas where we would like to make stuff to see what happens. So we will continually make new things to see if those new things do anything useful. I guess that's really the best way to put it. So if you start with uranium there, it's black and solid, and if you go class uranium with neptunium, it's a gray color. So that bottom row is all gray. This is the extension, right? Because that ends 103, and here's 104, 5, 6. And then this is an old table, the new periodic table's out all the way up to 118. All of those things are elements that we as humans have created. And like I said earlier, there's not very much use for it. We use plutonium for different things. We use americium for smoke detectors. So you know how that works? Americium is an alpha emitter. So you got a little plate inside your smoke detector that's got a little bit of painted americium on it. So it's constantly shooting off these alpha particles. Across from it, I've got another plate that's negatively charged, that when the alpha particle hits it, it counts that. Okay? So I've got this constant stream of alpha particles hitting this plate, and the alarm is fine, doesn't do anything. It says, okay, all the americium that I'm expecting to transfers. But then what happens if there's smoke? Blocks it, so it sets the alarm. It blocks it. So smoke gets in between these two plates, and the particle of alpha tries to get up to the plate where it's supposed to, and it runs into a smoke particle. And now the plate's like, hey, there's something in between us. The only possible thing that can be in between us is smoke, so I'm going to alarm, which is why you walk over, you just burn some bacon and you're like, shut up. So how does this help? We're getting smoke that's stuck in between two plates to move out of the way, and the smoke gets removed. So, yeah, but we don't have a lot of uses for this stuff. But we're hoping for, we come up with a new element and it's superconducting at room temperature. Like if we came up with a superconducting substance at room temperature, we wouldn't have to build any electrical plants for a long time. And why would that be the case? Because when the electricity runs through these wires, it produces heat, and that heat is energy that's lost. So when the dam sends electricity to California, it loses half of it on the way there. So if we could have it lose none of it on the way there, then it would be like we had 2 dams. So that's what we're doing. We're trying to make stuff for the sake of making stuff. And we would be way further along, except Ronald Reagan is an ass. There is a 10-mile circle underground in Texas that's been mothballed since the 80s. It was going to be the world's largest cyclotron. It would still be the world's largest cyclotron. Right now, the largest one is CERN in Europe. And it's basically just a thing where you can accelerate particles to very high speeds and slam them into each other. And there was going to be a ridiculous one there. But Reagan doesn't like science, and he didn't want progress, and the people who paid for his campaign didn't want progress. Same reason he ripped the solar panel off the White House the first day he came in, because oil guys gave him all of his money for his campaign. So we still have that thing sitting there, and it's ridiculous. Like if you look at pictures of it, you could put vehicles inside of there. It's so big, and it's still just sitting there in mothballs. And I mean, maybe we could have the substance, or maybe we could already have that superconducting substance at room temperature if we just kept working on it. But we have closed. I mean, if you looked at the names of those new elements, the ones that aren't shown up there, but they're on your periodic table, they're not American names. They're not English names. They're names of Russians and Chinese and Japanese, because they're still funding their cyclotrons and we're not. So yeah, basic research is important. Okay, that's it. See you guys on Monday.
We're done.
What?
But the cover's dry now, right?
Oh, you guys didn't weigh the copper, that's right.
Put 3 people.
The
couple issues for
the decanting method was length.
we took some liberties.
It's very thorough. There you go. I think that's how I can describe it.
There was, well, you remember that, but that didn't. Me either.